there are only 6 different arrangements for 3 reactors. So for each arrangement, you go through this procedure and you determine X out for each of those arrangements, and you pick the one that's the best. You don't usually have 20 reactors. It's usually a small number, 2 or 3. Bless you.
By using this method all the way under the curve, are you finding, in essence, finding the area under the curve?
Is there any place where I'm calculating an area? Do you see any area
Is there a way
calculation?
to make a connection between what you're doing there and finding?
I'm not calculating any areas here. The curve I calculate areas under is this curve, when I have a plug flow reactor. Minus 1 of RA equals 6. Plug flow reactor. These are CSTRs. In CSTRs, I never have a reason to calculate an area under curve, because there's no interval. Okay, and I just want to emphasize again that this straight line has a slope. I think if I rewrite it, it might be a little clearer. I have a slope, 1 over tau j, that's the slope. And the slope is delta y over delta x. Delta y is the y at the top of at the curve, minus 0. So it's minus RAJ over CA0, minus 0. So this y minus this y over delta x. Delta x is xj minus 1 over xj, minus xj. So I think maybe if I write it in this form, it's a little bit clearer that this straight line is a straight line that goes from 0, from the coordinates xj minus 1, 0, xj minus 1, 0, to the coordinates minus RA1, CA0, x1, minus RAJ over CA0, x1. And that has a slope 1 over tau j. So hopefully, if you may like this form or you may like this form I think might be a little bit clearer. And it's the way it shows you why this straight line of slope 1 over tau 1 connects this point with the appropriate point on the curve. Are there any questions? Okay, well, let's continue with that line of investigation. And let's look at this is a specific case of 2 CSTRs in series. So suppose I have 2 CSTRs in series. Well, why don't we say it differently? Suppose I want to build 2 CSTRs in series. Either build or if I have. I guess it could be either one. Should I make the first one bigger and the second one smaller, or the first one smaller and the second one bigger, or should I make them the same size? So, should either one be bigger? Bigger than the other? So let's look at that question. So remember, if we go back to the curves we've been drawing until now, minus 1 over RA versus XA. And we said that these curves typically look something like that. So if I have two, so here's in and out. So I'm going to have some sort of intermediate concentration. So I'm going to have two CSTRs in series. In, out, 1. And let's see graphically what I get here. For my taus, I have a tau 1 and a tau 2. And depending on where I put this point, x1, tau 1 is going to get skinnier, and tau 2 is going to get fatter if I move to the left, or vice versa. So when I say how should I divide up the volumes, the taus, I'm saying where should I put x1 to do the best? Remember, I want to make tau total as small as possible. So the goal here is to minimize tau 1 plus tau 2. Well, notice if I make a big rectangle here, the height of the rectangle is determined by the height of the endpoint, the right endpoint, because that's given. X out is given. X out is given. So if X out is given, the height of the rectangle is given, the width is given. So the rate function is known, X in and X out are known. So this big rectangle is known. And the way I minimize tau 1 plus tau 2 is by maximizing the piece I'm cutting out. So what I really want to do here, we maximize the area of this rectangle. So how do I maximize the area of a rectangle? First, let's do it in a generic way, and then we'll do it here. So if I have an area of a rectangle, it's sort of an x times a y. And if I want to maximize that, so it's a delta x times a delta y. X times y. So if I take dA, that's x dy plus y dx. And if I set this equal to 0, then this tells me that dy dx is equal to minus dy dx is minus y over x. So what this tells me is that the derivative dy dx should be equal to minus y over x. Y over x, or delta y over delta x, is the diagonal. This is y, this is x. Delta y over delta x. Delta y over delta x is this slope, this diagonal. And dy dx is the derivative here. So, of course, I didn't draw it as maximum yet, but this is telling me more or less that you want the diagonal to be equal to the derivative of the curve. So you want to move this point around until the diagonal is parallel to the derivative of the curve to do the best, to maximize this area. So obviously, I didn't draw it that way. It's not maximum yet. Well, why don't we look at a specific case? Well, actually, let me just give you a general conclusion here, and then we'll talk about how we get it. So, if n is equal to 1, if I have an nth order reaction, if n is equal to 1, the best is when V1 is equal to V2. If n is greater than 1, so if I have an nth order reaction where n is greater than 1, then now we have three cases: n equal 1, n greater than 1, n less than 1. Well, let's see what we expect to happen here. Why don't you help me with this one? If n is greater than 1, if n is bigger than 1, then the rate is very strongly dependent on the concentration. So if I make, so what I would like to do is I would like to keep the concentration high as long as possible. Now, if I take two reactors in series, if the first reactor is really big, then the concentration will drop from the inlet concentration to the outlet concentration of the first reactor. If that reactor is really big, meaning has a big tau, that outlet concentration is going to be really low. If that reactor is small, then that outlet concentration is still going to be pretty high. So which do you think, and if the rate is very sensitive, because n is greater than 1, which do you think I want to do? Do I want the outlet concentration of the first reactor to be high or low? High. So I accomplish that with a small first reactor. So here I have V1 is less than V2. When n equals to 1, we're going to show that the best you can do is when they're equal sized. When n is less than 1, there's much less of a sensitivity, because it's sublinear. And it turns out that you do better if V1 is greater than V2. So why don't we look specifically at this case for an nth order reaction and see what we can get. Now, in practice, unless there's a very big difference in the predicted volumes, it's usually cheaper to build two equal-sized reactors than to build two reactors of different sizes. So even if you're getting an ideal answer where one reactor is a little smaller or a little bigger than the other, it's not clear that it economically makes sense to build two different reactors, two different sized reactors. Okay, so let's look at this area. If I have an nth order reaction, then let's write delta y and delta x. Delta x is just x1 minus x in. And delta y is 1 over, it's the height, minus 1 over RA2 over minus 1 over RA1. And for an nth order reaction, this is x1 minus x in times 1 over, now an nth order reaction, minus RA for an nth order reaction is equal to what? You weren't paying attention. That's not an excuse. Next time I ask somebody, this goes for the whole semester, a simple question and they tell me I wasn't paying attention, or they don't know what the question was, or they ask me to repeat the question as a stalling tactic, I'm going to ask them to leave. Okay? Your job is to listen. Everything's in the textbook. If you like copying, you can copy the whole textbook. You can do that on your own time. You're here in class to listen and to learn, not to copy. If you want to copy, you can go to secretarial school. Secretarial schools, secretaries learn to copy. You have to learn to think. This is an engineering class. Thinking is more important than copying.
K times
K times
CH.
CA. And what is that in terms of x? Let's make this our constant density. What is this in terms of x?
CA0 is 1 minus x.
Yeah. It's not a trick question. Okay, so okay, and then so here I have CA0 to the n, 1 minus x a 2 to the n, 1 over 1 minus x a 1 to the n. And I'd like to work out the specific case. Well, actually, this is all right. And I'm going to choose the reference state as the inlet here. So I'm going to choose this as the reference. As x in is equal to 0. So if the inlet is the reference state, then x in is equal to 0. I can choose any reference state I like. So this is equal to x1 over CA0 to the n times 1 minus x2 to the n, 1 minus 1 over xa, 1. And let's go ahead and do this maximization. Yeah. So let's do So let's take dA dxa1, because that's the variable is xa1. So let's see what I get. And so I have 1 over CA0 to the n. And now I take a derivative with respect to xa1. So I've got an xa1 here and I've got an xa1 here. So then first let's take the derivative of this thing with respect to xa1 and just get 1. So that's 1 over 1 minus xa2 to the n minus 1 over 1 minus xa1 to the n. Minus, plus xa1 times the derivative of this thing with respect to xa1. There are no xa1s in here, so what's the derivative? What's ddx1 of this? 0. Okay, then I have ddxa1 of this.
1 over minus, so 1 over 1 minus 1 divided by 1 minus x makes it 1 and
This is high school calculus. I see I have to ask everyone in class to get a high school calculus question. What's the derivative of this? I can't hear you when you move your mouth and no sound comes out. Wait, no, you went through that road. You already answered. So.
1 minus n
1 minus n?
raised to the power of 1 minus n. 1 over 1 minus xa1 to the power of 1 minus n.
I'm sorry. Minus, now I'm getting confused. So it's minus n back to minus n plus 1. This is minus n plus 1 and minus 1. Right? Now I'm getting it. Okay. So I've got the derivative of 1 minus x to the minus n. So this is minus n, 1 minus x to the minus n plus 1. Minus n minus 1. Times a minus 1. Okay, so I've got an n over 1 minus x a1 to the n plus 1. And let's just make you see what we get with minus signs. So the minus sign still stays, because I had a minus from taking the derivative and another minus from the chain rule. Okay, so let's set this thing equal to 0, and let's see what we get. So I have, I set this equal to 0, I can cancel that. I have 1 over 1 minus XA2, and that's equal to, okay, I've got 1 over 1 minus XA1 to the n times 1 minus NXA1 over 1 minus XA1. It's 1 over 1 minus XA2. And that doesn't look right. Actually, why don't we just multiply through, actually it may be okay. Why don't we multiply through by 1 minus XA1 to the n. So I have 1 minus XA1 to the n over 1 minus XA2 is equal to, so I multiply it out, and then I'm left with 1 minus XA1 minus this. So it's n plus 1 XA1.
That sign should be changed.
In the first expression, you have minus 1 over RA2 minus 1 over minus RA1. So it should be a plus.
What should be a plus?
Where it says nth order?
Yeah, minus,
Yeah.
this is positive and this is positive.
The line where you have dxa over xa1, the sign should be changed on the xa1.
Which line are you talking about?
The 1, 2, 3, 4th line.
Uh-huh.
That sign should be changed. It should be plus xa1 n over 1 minus xa2 n plus 1.
A dxa1. I'm sorry?
It should be plus xa1 n over 1 minus xa2 n plus 1.
Let's see. So I've got the derivative of this, which is 1 times this, plus this times the derivative of this. The derivative of this is 0. The derivative of this, I have the minus sign here, and I take the derivative of this, it's still minus.
That derivative is negative.
Minus n coming down, and then another minus from the chain rule. So I have 3 minuses, it gives me a minus. Okay, let's just see if this is the right answer. Okay, something was missing. Yeah, one thing that's missing was there was an n here. I lost the n. So this should be to the n. And why don't we go back to this equation here. So I'm going to go back to this equation just to okay, set it equal to 0. So here I have 1 over 1 minus xa2 to the n is equal to 1 over 1 minus xa1 to the n minus nxa1 plus nxa1 over 1 minus xa1 to the n plus 1. And now I'm just going to multiply through by 1 minus xa1 to the n plus 1. 1 minus xa1 to the n plus 1 over 1 minus xa2 is equal to 1 minus xa1. Because when I multiply to the n plus 1, the n's cancel and just does with 1 power. And then I have plus nxa1, which is just equal to 1 plus n minus 1 xa1. And let's see if that's correct. I do have the answer. That's correct. Okay, so this is the equation one has to solve. And this is a polynomial equation. It's an n plus first order polynomial. For the only unknown, which is xa1, xa2 is known. It's the outlet conversion. The order of reaction is known. The only thing that's unknown is xa1. So notice here xa1 is linear, but here I have it to the n plus first power. So this is a polynomial equation of the n plus first order. Now if n is equal to 1, a first order reaction, I just get a quadratic, which I can solve. So why don't we just solve the quadratic equation? So let's look at n is equal to 1. So for n is equal to 1, I have a quadratic. And that's just 1 minus x1 squared over 1 minus x2. Did I lose an nth power here? There was an nth power. But x2 is known. Is equal to 1 plus n minus 1 x1. So I have 1 minus x2 squared. Well, let's multiply 1 minus x1 squared, which is 1 plus x1 squared plus 2x1, is equal to 1 plus n minus 1. Now in this case, when n is equal to 1, n minus 1 is 0. So then I just get 1 plus 1 minus x2, 1 times 1 minus x2 squared.
I think it should just be to the power 1.
Yeah, the power.
Because the denominator is
Yeah,
just
it's the first. Okay. This is to the end. First. Okay, so I have x1 squared plus 2x1 plus 1 minus 1 minus x2. So the 1 minus cancels, and the minuses cancel. I just have x2 equals 0. So I have x1 is equal to minus 2 plus or minus the square root of 4 minus 4x2 over 2, which is equal to x1 is equal to minus 1 plus or minus the square root of 1 minus x2. Is it the plus or the minus here? I'm sorry?
The second equation should be a minus 2x1.
Minus 2x1. Yes, make it minus 2x1. So 2 plus or minus the square root. Yeah, that's plus 1. Thank you. So do I take the plus sign or the minus sign? Why do I take the plus? Right. So I have 1 plus the square root of 1 minus x2. So we'll analyze this next time. I just want to get that expression. Are there any questions? We're done. Are there any questions? Okay, homework?